Hey, what's up guys? Welcome to the first and last episode of No Physics Math lecture video. Today we will talk about physics. Nope. We will talk about how easy physics is if you are good at math. So let's talk about electrical circuit. We all know there are DC and AC. Since we are not speaking to secondary students, let's start on AC straight away. This is a voltage time AC graph. We mathematicians do not like this graph because math is not straight. Let's talk about graph like this. What does it look like? A sine graph? Nope. It's actually a cosine graph. Okay, whether it's sine or cosine, we give any electrical signal of this shape a name. Sinusoid. So why are we interested in sinusoid? Because nature is characteristically sinusoidal, and Fourier analysis shows that any practical periodic signal can be represented by a sum of sinusoids. So expression for this sinusoid will be Vt equals to sine t. We can scale it along y direction by a factor Vm. So Vm will be the amplitude of the sinusoid. We can also scale it along x direction by a factor omega. So omega will be the angular frequency of the sinusoid. You will know why it's called this. We all know sine graph has a period of 2 pi. So we can see from our sinusoid that omega t equals to 2 pi, where t is the time taken for one cycle. Thus t equals to 2 pi over omega. However, usually we don't talk about t. We talk about its reciprocal f, the frequency. It has a well-known unit, hertz. Thus, clearly, omega equals to 2 pi fo. We can also translate the graph along x direction by factor phi, so phi is called the phase of the sinusoid. Now let's make things more complicated. Mathematicians love to do that. We introduce phasor representation of sinusoids. A phasor is a complex number representing the amplitude and phase of an sinusoid. Take a complex number z equals to x plus iy. Here I is the square root of -1. Some engineers use j instead of I because people may confuse it with capital I, which is current. But they don't know if we capitalize the I in this sentence, it clearly has a grammatical error. Thus we mathematicians will stick to our beloved symbol, I. Complex number can also be written in exponential form. Okay, assuming your ignorance about complex number, let's have a crash course first before we proceed. You can think of complex number as nothing but a point on a 2D plane, but the x-axis will now be real axis, which represent the real part of z, which is x. The unit of y-axis will be root -1. And its coordinate will be the imaginary part of z, which is y. So x plus iy will be a point on the complex plane with coordinate xy. Now take a look at this formula. I believe everyone has seen this formula before. It is the most beautiful formula in mathematics called Euler's formula. How does this formula work? Yes, I'm not going to explain to you. You can check our video on Euler's formula to have a concrete understanding. If not, don't you know YouTube is meant for dummy? In short, in the complex plane, e to the power of theta I is equivalent to rotate this line on real axis of length 1, theta radians anticlockwise. So in the complex plane, angle theta equals to e to the power of I theta. If we multiply this number with k, just extend this line accordingly. Thus, we let our complex number z be our e to the power of I phi. We also know z equals to x plus iy. Thus we can see from the graph that x equals to r cosine phi, y equals to r sine phi. So we have e to the power of I phi equals to r times sum of cosine phi and I sine phi. So we are safe to say that cosine phi equals to x, which is the real part of e to the power of I phi, and sine phi equals to y, which is the imaginary part of e to the power of I phi. So now our sinusoid Vt equals to Vm cosine omega t plus phi equals to the real part of Vm e to the power of I times omega t plus phi. Manipulate the damn Greek symbols. Now we use a single v to represent this whole chunk. So this v will be Vm e to the power of I phi, or even shorter, Vm angle phi. This v is finally the phasor representation we were looking for, a complex representation of the amplitude and phase of a sinusoid. One way to visualize phasor is to imagine a water pump in a complex plane. The center of the wheel is at the origin. The wheel has radius Vm and is rotating at angular velocity omega. Remember, omega is called angular frequency in sinusoid. Voltage Vt now becomes the length of water being pumped in or out, which is also the projection of the rotating radius onto the real axis. Thus Vt equals to Vm angle theta. We know the angular velocity of the wheel is omega, so angle theta in complex plane will be e to the power of I times omega t plus initial angle phi, and from here we can get back our lovely phasor again. Okay, now I believe you have a great understanding of phasor. Next episode we will talk about phasor relationships for circuit elements, so we will assume you understand what resistor, capacitor, and inductor are. A quick spoiler. Capacitor is an element designed to store energy in its electric field. The amount of charge stored Q is equals to C times voltage V. Here C is constant, which is known as the capacitance of the capacitor. Q is also the integral of I, which is the current, with respect to time. So we have our voltage current relationship for capacitor being V equals to 1 over C times the integral of I dt. Pretty straightforward, right? Okay, a bit of challenges. Can you verify if the voltage current relationship for resistor in phasor representation still follows Ohm's law? If you can do this, you can also try to discover the voltage current relationship in phasor representation for capacitor. Okay, that's it for today's episode. Thank you very much. We look forward to you in our imaginary next episode. See ya.